She was working on discrete approaches to quantum gravity with Jan Ambjorn, and now she's a Lise Meitner Fellow in Vienna.
Yes, almost. The Lise Meitner unfortunately ran out in March, but I'm still in Vienna as a postdoc. Okay. I probably should update my website. Okay, hello, great to see you. I thank the organizers very much for making this possible. It's great to actually give a talk in front of an audience again. So my talk title is A Picture of a Spectral Triple. Although that is the second half of the talk, because after the talks yesterday and today, I realized I've done some work in the past that is actually much more relevant maybe for the audience here than what I originally thought I'd be talking about. So I reshuffled my slides a little bit and thought I'd do that instead. The rough outline for my talk is I'll start with a motivation. In my case, the motivation is quantum gravity, or maybe path integrals over geometry. Then I talk about fuzzy spaces and how fuzzy spaces, when you take a path integral over them, can lead to interesting multi-matrix models, which I think is where people here might have some input. And then in the end, I'll still talk about painting a picture, but that part of the talk might get accelerated a bit depending on how much time everything else beforehand has taken. I know it's a little bit awkward, but please interrupt with questions. Just wait until the microphone comes to you in case you're here so that the audience on Zoom can also hear. Good. Now, what I'm trying to do, I like to do computer simulations. In particular, Monte Carlo simulations. If someone asks about that, I do have backup slides to explain Monte Carlo method really quickly. What I want to do is a path integral over geometries to do quantum gravity with that. Now, how do I do that? Well, it's really, really easy. You define a theory, you pick some observables, and then you pick the algorithm to calculate. Well, my theory gets defined by figuring out how do I want to parameterize the geometries I'm integrating over. When I'm doing spectral triples, I want to integrate over the Dirac operator. That gives me the information of the geometry that I'd need to integrate over. What observables can I measure? Well, observable, it's a physicist's word. Of course, nothing of what I'm talking about is actually observable, but it's things that I can calculate expectation values of. And basically, any function of the geometry I can pick as an observable. So anything that we write down, I could try and measure here. Of course, with a little caveat that anything I want to measure, I need to be able to compute on my computer in a reasonable amount of time. Because even if I can calculate it quickly enough for a single geometry, it might be different when I'm doing my simulations and have to calculate it for several different geometries to get an expectation value. So there's a little bit of thinking involved in there, and it's actually one of the harder parts. And the last bit is pick your algorithm. How are you going to compute that? In my case, I'm using Metropolis Markov chain Metropolis algorithm. Relatively simple. There are better algorithms out there. I've started implementing them. I also know of other people that have implemented those, but haven't published their work yet, which is always frustrating to wait for. Now, I'm going to use geometries as spectral triples. So here is the definition of spectral triples. You're all familiar from Walter's talk earlier, probably, but this is just, again, in different words. So I'll need an algebra with an action on a Hilbert space and a Dirac operator D. The nth characteristic value of the resolvent of the Dirac operator is of the order n to the -1 over p. That is basically saying that your dimension of the space will be p. The next condition is the so-called first order condition. This is what makes your Dirac operator be a first order differential operator when you go to the continuum. Another way to say it is that you've got a left algebra action and a right algebra action, and your Dirac operator consists of a left acting part and can also have a right acting part, but it can't have a part that is left acting and right acting at the same time. We're going to use this later for the fuzzy spaces to parameterize the Dirac operator through matrices. That is why this is of interest. And then condition 3 about a domain that is just about the boundedness of the Dirac operator. And then Hochschild cycles and a module space. They are there for completeness because they kind of belong there. Please don't ask me about them. A little aside, because this is something where I kept spending a lot of time trying to pick this apart, and I thought maybe some of the participants here would also might also help having it said once. So you have spectral triples. A spectral triple can be a Riemannian manifold with a spin C structure. A spectral triple can also be a non-commutative geometry, or spectral triples can be a lot of different things too. You can do Cantor sets, you can do graphs. So there are many different things you can do as spectral triples. So spectral triple is not necessarily equal to non-commutative geometry. On the other hand, if you have a non-commutative geometry, that isn't necessarily the same as a spectral triple. In fact, if you're talking to a physicist and they are telling you about non-commutative geometry, and you tell them, oh yes, spectral triples, great, I heard about that, you're very likely to get very confused looks. For physicists, the closest to how spectral triples are for non-commutative geometry are matrix geometries, which we've seen the matrix models. So you can have those things. There's also a lot of other more phenomenological motivated, like just introduce an just introduce a commutator between space and momentum that is not, oh wait, no, not space and momentum, between different directions in space that is non-trivial. So you can do a lot of things that you can call non-commutative geometry that are not necessarily connected to non-commutative geometry with spectral triples. So check before you before you get into confusion there. Of course, some of these physicists' non-commutative geometries, for example, the fuzzy sphere was something that has been done by physicists for a long time already. And a fuzzy sphere can actually also be written as a spectral triple. So some physicists' non-commutative geometries are spectral triples. There might be others where you can still find a way to write it, but a spectral triple has a lot of other structure that might not necessarily be given. So always ask people for their definitions before you start trying to compare. Good. Now, we've heard about spectral triples, and I thought I'll show you my favorite simple examples of spectral triples. We had a few examples in Walter's talk earlier, but this is actually the simplest possible spectral triple that you can write down. It's really just the circle as an algebra. So we've got a unitary operator U that's act on a Hilbert space of square integrable functions on the circle. The operator is unitary, and you can then see your operator is unitary, your Dirac operator is self-adjoint. Now, if you are applying the commutator of the Dirac with the unitary, you see that actually you'll get this kind of relation, and from this relation you get that your eigenvalues that you can generate all of your higher eigenvectors by applying U. So you can generate the entire algebra just by powers of U. And then you've got a spectral triple, which are all smooth functions on the circle. That's your algebra. You've got the square integrable functions on the circle. That's your Hilbert space. And your differential is just minus I d by d phi. So that's along the angle of the circle. That is the very simplest spectral triple you can write for geometry. Now you can make it a little more complicated and get to the non-commutative part. And that is, you just say, okay, let's take two of those circles and put them together with two generators, and then you've got a torus. And now that you've got two generators, you can introduce a non-commutativity. In the very easiest case, you're just saying, okay, UV is the same as VU times some phase factor. You can still generate the algebra. Now you need to keep track of which order you're putting them in, but by changing order, you're just changing your prefactors. But now you've got a non-commutative spectral triple, and your algebra are functions on the non-commutative torus. And so your Dirac operator, because it's two-dimensional, you've got the Pauli matrices in there. So this is the simplest non-commutative spectral triple. Now, I want to do spectral triples as quantum geometries. I mean, you can probably, if you've even heard a little bit of quantum mechanics, see why that's attractive. Quantum mechanics, you've got a lot of Hilbert spaces, you've got a lot of algebras. All of these things are already there. So sounds coherent, sounds like it should work well. Well, personally, I prefer my spacetimes discrete. There's just something about smooth spacetime that's a little bit weird. Maybe I should also point out, I'm saying spacetime right now. Spacetime spectral triples are, of course, a whole different kettle of fish and much more complicated because Lorentzian things are basically annoying, so we forget they exist. Now, if I want to do a spectral triple but have finite spacetimes, there are two possible things that I could do. On the one hand, I could take the fuzzy spaces. Fuzzy spaces, there are a few known, fuzzy sphere, fuzzy CPNs, fuzzy torus. They work great for very, very symmetric spaces. On the other hand, I have not heard of, well, I've heard of a fuzzy ellipsoid. To be precise, I've heard of a PhD student despairing trying to find one. In a fuzzy space, you've got a finite algebra, and then you can find a Dirac operator that works with that finite algebra. So this is, it's all finite, everything works still together. The other option is to say, okay, my spectral triple is just a truncation of an infinite spectral triple. That is what Walter also mentioned, the operator spectral triples, which he's working on, because even if spacetime is fundamentally smooth, we'll never be able to measure infinitely many modes of spacetime. So we better figure out how to work with finite measurements if we ever want to make connection to measurements. And the truncations, you truncate your algebra and your Hilbert space to make them finite, and then you truncate the Dirac operator in a compatible way. While doing that, you usually break the first order condition. So, okay. Originally, I would have talked about some simulations with truncations of spectral triples, but I changed my mind about fuzzy spaces because here we get fun matrix models. Now, a fuzzy space as a spectral triple is okay, this is not only a spectral triple, this is a real spectral triple. So it's got S, which is its KO dimension. It's got a Hilbert space and an algebra and a Dirac operator. It also has a chirality operator and a real structure. The algebra for a fuzzy space are really just n by n complex matrices. Possibly, if you're picking a particular fuzzy space, it's just a subset of these matrices, but it's matrices. So you see why I like that. My computer knows what matrices are and how to work with them. They're acting on a Hilbert space, which is a Clifford module tensored with matrices. You see how this makes my life easy again, because Clifford module, vectors, numbers, I can write it all down. Matrices, I can do matrix multiplications. Other people have implemented very fast matrix multiplications for me, so I don't have to worry about that. This is perfect. Now, V is a PQ Clifford module. So you've got gamma matrices, P with a positive sign, Q with a negative sign, I think, or the other way around. It's a sign, it's not so bad. So the KO dimension just tells you Q minus P modulo 8. That is because Clifford modules have this periodicity. I recently learned that some people have called this Spinorial chessboard because they just keep repeating the same signs for things. So basically knowing S tells you how certain commutators behave. Among them, the commutator of the chirality and the real structure with things. So now your chirality really just acts as with the chirality operator on the Clifford module, and the real structure acts as charge conjugation on the Clifford module and as Hermitian conjugation on your matrices. What the real structure also allows you, which I haven't really written down here, is that your real structure allows you to define a right action from the left action and the other way around. So that means that you can go from right multiplication to left multiplication by applying your real structure. That's what the self-adjoint thing does here. Now, a simple example for a fuzzy space would be the fuzzy sphere. Before we do a fuzzy sphere, here's a quick look at the continuum sphere. Your algebra is SU2. Your Hilbert space are the sphere integrable functions on the sphere. I think the second thing should be a C. I don't know why there's an S. So complex square integrable functions on the sphere. And your Dirac operator, Pauli matrices times derivative operator plus a spin connection, omega mu nu.
Maybe this S refers to the spinor bundle. Second S, yes?
Possible. I'm not sure what I was thinking when I wrote it there anymore. Could also be that I was thinking, oh, S, I'll define as the field over which I want to define this. So,
okay.
But, okay. Now the fuzzy sphere is a finite spectral triple that approximates the continuum sphere. That means that your algebra of SU2 becomes n by n complex matrices. And a natural basis for these matrices here are then the irreducible representations of SU2 up to spin j. So j equal 1/2 n minus 1. That is how high the spin. You see, we've cut off the matrix size. Now we can only get up to a certain spin in our states. Your Hilbert space are the spinors on the sphere, which are C4 cross MNC. And your Dirac operator now has, down here, it's identity plus a sum over a product of two Clifford, of two Pauli matrices times LJK, and LJK is the Lie algebra generators of SO3. So this is the fuzzy sphere with, to be precise, the Gross-Presnyder Dirac operator on it. There are different Dirac operators for the fuzzy sphere. You can write them differently. Now, you can maybe already see I've written the Dirac operator in this case, and it's basically a matrix, and matrices I can integrate over. Now, we can do this a little bit more general by looking at if I'm saying I want a fuzzy space that satisfies the axioms of a spectral triple. What are the axioms my Dirac operator needs to satisfy? And can I, from there, parameterize so that I only have the degrees of freedom that don't violate my axioms? So the conditions for the Dirac operator on a real spectral triple are that it needs to be self-adjoint, it commutes or anti-commutes with the chirality. If it commutes or anti-commutes, that is one of those things where the KO dimension comes in. It also commutes or anti-commutes with the real structure, again, depending on the KO dimension. And then it needs to satisfy the first order condition. So it needs, if I'm taking the commutator with the Dirac of a right acting element and a left acting element, it comes out as 0. Now, if we take all of these conditions and apply them in the fuzzy space where we know what the algebra looks like, we know what all of these things look like, what comes out is that my Dirac operator is actually pretty constrained. My Dirac operator is a sum of elements where you've got omega I, which is a product of the gamma matrices on your Clifford module, and then tensored with a left acting part and a right acting part for some matrices Ki. And omega I, there's, depending on how many how many gamma matrices your Clifford module has. They only span a certain number of omega I, so there's a limit to how many terms you have here. And then you've only got those matrices for your Dirac operator. This is work by John Barrett, by the way. Now, that means I've got a finite number of matrices in my Dirac operator. That means I can just integrate over these matrices and write down a nice matrix model. So I already said I want to do a path integral over fuzzy spaces. Well, I can integrate over the Dirac operators by just integrating over the matrices K. When I'm doing that, as a physicist, I need to add an action. I call it an action. You might prefer calling it a measure. In any case, I want to put an exponential with some kind of weight that depends on my matrices in there. The idea that someone working on non-commutative geometry maybe thinks of first is probably the Kohn-Shamsuddin action, which can give you the standard model, and I think Walter might mention it tomorrow. That has one big problem. The Kohn-Shamsuddin action actually goes to 0 as your matrices go to infinity, which is formally fine. But if I tell that to my computer just starts integrating over matrices and wanders off towards infinity and nothing ever converges. So I can't put that on my computer and expect to get results in a finite amount of time. Instead, we figured out, okay, let's put the simplest possible action. So we take a coupling G2 plus trace D squared plus trace D to the 4. I could also add a coupling in front of trace D4, but actually that I could just get rid of by a rescaling. So it's wouldn't change anything. Why do I put the coupling in front of trace D squared instead of trace D4? Because trace D squared, I can change the sign. I can have positive or negative additions there. Negative, then I get some kind of a Mexican hat potential, known and beloved to all the physicists. But if I change the sign on trace D4, I again get the problem that nothing converges, and so my computer will run very, very long without telling me anything I want to hear. So I can also motivate doing this kind of action actually physically, because the lowest order expansion of anything when you're doing a Taylor expansion will be around, well, lowest order expansion around a local minimum will be trace D squared. You could have D3 terms, but in this case, they normally fall away. And then plus trace D4. Yeah, it's bounded from below and it rises nice and quickly to infinity. So my simulations don't have to probe so much space.
Excuse me, but this coupling constant somehow depends on the n or not?
No, we did not define the coupling constant to depend on n.
So it is fixed once and for all, yes? It is fixed once for all, yes?
We probe at different coupling constants. And if we are probing it, and there'll be slide plots about it later, if we're probing that, we can then see how the critical point move, well, the probable critical point.
Okay, so you fix a coupling constant, then you let n go to infinity, you are looking what's happening, and then you can change this coupling constant and run this experiment once more, yes?
No, we can't do n to infinity. Again, that's not what the computer does. I can at fixed n and fixed g calculate expectations values for different things. For example, for the spectrum of the operator or the action or the variance of the action.
Okay, I see. The trace would diverge, obviously. Sure, sorry.
Yes, so if I wanted to probe for higher n, I would then have to see how does the critical point scale with n. I did actually do that. I don't have that on my slides today, but I have the reference. If I remember, I'll say it. Okay, now this is the action written in terms of the Dirac operator. I can also write the action in terms of the matrices that my Dirac operator consists of. Now, here I've got the 2-0 geometry. So obviously 2-0, that is PQ, that's the Clifford module I'm working on. And 2-0 is nice and easy. We only have two anti-commutators and two Hermitian matrices, H1 and H2. If I'm taking the trace of the Dirac operator squared and the trace of the Dirac operator to the 4th power with these matrices, what I actually find is this, well, matrix model. And you see that now I've got the trace of H1 squared, but I also have the trace of H1 squared. And then I've got trace H1 to the 4th, mixed traces, but I also get trace H1 times trace H1 to the power of 3. And trace H1 squared, and here's trace H1, H2 squared. And I get almost any type of mixing. And in particular, those multi-trace terms are usually something which doesn't work so well in the analytic work about matrix models that I've seen. But it is a matrix model. It's just a pretty weird and complicated one. So. Right, and I should say here that Carlos has done a bunch of work on solving those analytically. So that's what he mentioned yesterday. Right, now when I'm doing simulations like that, what I'm trying to do is look for phase transition, because phase transitions are something physicists get very excited about. Also, if you want to take a limit n to infinity, your phase transition is the point where you normally expect to be doing that, because at a higher order phase transition, you have divergent correlation lengths. So even if your system size goes to infinity, you still will get nice behavior. One possible marker for phase transition is a peak in the variance of your action. And you'd expect it to get sharper when your system gets larger. And higher order phase transitions should show signs of correlations. So by the way, this is the paper where I'm looking at the scaling. So there I'm looking at how the critical point scale with n, which would be the relevant part. Now, I really just wanted to quickly show this here. So I did different system sizes, and you can see my peak definitely gets sharper. I can calculate where the critical point is. And I can also look at correlation between eigenvalues. And this is before the phase transition and after the phase transition. There, the correlations are not very strong. They're mostly along the diagonal, which makes sense. You'd expect eigenvalue to be strongly correlated with itself and maybe somewhat correlated with the neighbors. But at the phase transition, you see this large blob where everything is correlated. Now, system size n equal 5 and system size n equal 10. For technical reasons, n equal 10, that is the matrix size of the H by H matrices. That actually means that my Dirac operator has something like 400 eigenvalues. So because the H matrices are left acting and right acting, and you've got the Clifford module part in front. So this gets large. So this is kind of nice and looks like we might have a phase transition. And there's some very interesting work by a PhD student of John Barrett, which is writing up right now. So I'm hoping that he has done some more work on these weird multi-matrix models. And that's the first part of the talk. Did we start on time or? Okay, I don't want to bore you. If you think I should stop right now and we need to go drinking.
No, I think you have at least half an hour.
Okay, perfect. Then now comes the second part of the talk, which is slightly disconnected. Also, I'm still talking about spectral triples. Now I'm talking about trying to paint a picture from a spectral triple. I've got a spectral triple, and I know I can calculate distances on the spectral triple for points, but can I actually take my spectral triple and turn it back into a geometry in a picture of a geometry? at least approximately, because if I'm doing this on my computer, then of course I will be doing some kind of truncation, so I just have a finite amount of information. Well, the answer is obviously yes, otherwise I probably wouldn't give the talk. Now, we've seen the distance between states in Walter's talk already, so I don't need to explain it that much, but between two states, I can do a distance by a supremum over all algebra elements, where the Dirac operator with the algebra element is smaller or equal to 1. Now, if we can actually calculate this numerically, we can plot our geometry. What does calculating this numerically mean? That means I need to find a bunch of states, and then I need to calculate the distances between those states. And then I've got a have a matrix with all of the distances between the points. And then there are well-established algorithms that will go ahead and just from the distances between points, embed those points into R3 or whatever you'd like and make a picture of that. So, okay, there's a question on here, which is from a former variation of the talk. Maybe we can see the difference between the two Dirac operators. In the other version, I would have had two different Dirac operators, which will show up again. Basically, we found a weird additional solution for a so-called Heisenberg relation, something that was supposed to only be solved by unions of spheres. And in the truncated case, we found an additional solution. And in the truncated case, it is as good as the sphere. Only in the truncated case, because in the non-truncated case, it violates the first order condition. But once you truncate, everything violates first order, so it's no longer relevant. And then it looks actually better than the sphere. And we were wondering, how can we compare that to the sphere? And that was what motivated us to say, let's make a picture. Also, pictures are pretty. I like having pretty pictures in my talks. Now, if I want to do the distance between states, the first part I need will be states. So we need to find some kind of states that are, in some sense, good, that are point-like. We decided to go with small dispersion states and then use the distance between them to build a picture. Now, what do we mean by, okay. Before I get to what are the states. When I'm taking the supremum over algebra elements from a spectral triple, I need to figure out how do I, for the given spectral triple, write down my algebra elements. I'm actually, this will be later, there's some generalization, but in the original work, we just decided, okay, the Dirac operators that we're trying to compare are actually a truncated sphere and an operator that has the same eigenstates as the truncated sphere. So since we know that it works with the same eigenstates, that makes it pretty easy. We can say, okay, let's take the truncated spherical harmonics as a basis for my algebra. That's just a very easy answer in this case, and it will not work well in general, but in this case, that gave us something easy to optimize over. And then we need to decide for the coherent states. Sorry, I'm gonna take off the microphone. I have to. This is the time for questions.
What do you call truncated spherical harmonics? What do you call truncated spherical harmonics?
Okay. Yes. So I can, for the continuous sphere, calculate the spherical harmonics, and then I can calculate the eigenvectors up to the eigenvalue at which I've calculated, and then turn the spherical harmonics into matrices in the eigenbases that I've so generated. Good. Okay, now the question of states, what states omega can I use? we worked inspired by the coherent states that Lukas Schneider-Bauer and Harald Steinacker used to do pictures of fuzzy spaces, but these were fuzzy spaces that are not spectral triples. Instead, those were motivated from string theory and are being probed by brains. We started from there, and I still, okay.
Sorry, could you quickly explain what is a coherent state?
Yes, I was expecting that to be on the slide, but I think it's a slide. It will happen. It's just not on the slide where I was expecting it. Just okay. Answer forthcoming. I'll get through the slides in the order I put them in. Okay, now when I'm doing the distance, I want to take the supremum over algebra elements. Technically implementing that, I can parameterize my algebra elements by taking some basis over the algebra elements and write them all as linear combination. And then I can tell the computer to please optimize over the CI and also include the constraint CI. Include the constraint here by calculating the CI. So this is a problem that my computer can actually solve pretty nicely. That's good. Now, that's the question. What are coherent states? Coherent states are states with low dispersion. And the dispersion for the algebra elements I can define like this. So it's the in physics terms, it would be the expectation value of algebra element squared minus expectation value of algebra element squared. And again, I have to take a supremum over the algebra elements, and I have to take a minimum over my states. So a low dispersion state is a state where for the algebra elements that gives the largest dispersion for the state has the lowest dispersion among all states. You see, this is already hard to state. This is actually something my computer doesn't like. It's a non-convex double optimization problem. And that does not work well unless I have something really, really simple I can do it on. There's also an additional sub-problem, which is even if we can find the solutions, these states are supposed to be points. But right now, it'll generate us points at random on the sphere. Except it won't really be random. It'll be biased by what my algorithm does. So I might end up with a lot of points at the North Pole and no single point probing the South Pole. So these are two problems that we needed to overcome. The first problem was how can we generate the algebra elements? Well, how can we get around the optimization of our algebra elements? The answer to that are so-called embedding maps. They can be motivated by the Heisenberg relation, which we were probing in the simulations first. Basically, these are things that work like coordinates for what we're doing. These are coordinates that will embed to the sphere. So we have put in a bias towards the sphere here, but it's okay because, well, it's not going to be the optimal states maybe, but they will be good enough and we can actually see how it's bounding things. So it will be okay. The next problem is our states should be distributed evenly. What do you do if you want things to not cluster together? You make them repulsive. So we add a little Coulomb potential to the end of the thing, and then our states will start distributing themselves evenly around. And with that, everything is easy now. We find a set of coherent states that minimize this dispersion, and then we can plug them in the distance equation and get our points. I would have finished at this point, but I was working with Abel Stern, who is actually a mathematician. So, okay, first come the pictures, then comes the actual mathematics that tells us that our states are actually points and our points are actually states. So here is a little picture of what the repulsive potential does. As you can see, if I did not have the repulsive potential, all of my points just show up at the same spot. But then even with a relatively low repulsive potential, they are well distributed. So this is, that's good. Now, right. We've said that this is a good definition for states, and that these low dispersion states should work well to approximate points. Can we actually show that in the limit of, if there was a limit that takes our truncation to a spectral triple that is a Riemannian geometry, if such a limit existed, that then these states would become points? And yes, we can show that states are points. So by saying that our state V has a barycenter, BFV, that is localized somewhere. And then we see that there's a map that the distance, lambda is a truncation. So the distance in my truncated space minus the distance of the barycenter of the states on the manifold goes like square root of the dispersion of the states. So the states, my states will converge to points. That's good. That's the first half of it. The second half is points are states. So I've shown you that if I have those states, the states will become points. But now I might have points on my manifold that I can't describe as such a state. So I have to be careful and go and look that all points are states. Now, each point x can be approximated through a state with a small dispersion and with a barycenter BV close to x. Okay. Now, okay. This is why I was so confused by maps, because here a map is something different than the maps in the topological recursion lecture. But basically it says that you can define all the necessary maps to make this work, and that everything will always be converging up to lambda, and lambda is the largest eigenvalue that your truncation retains. So this works well in that case. Good. Now, we've done the mathematics. I want to get back to making pictures. So this is a picture of, I've generated states for different truncations. How do these states look? How does the dispersion of the states look? And well, for lambda equal 4, you can kind of see it's pretty fuzzy. Even so, it's a low dispersion state. In this case, it's still very large, which you'd expect, because up to the eigenvalue of 4, that's not that much information you have about your geometry. Now, if you have lambda equal 10, you've got a lot more information and it gets tighter. And then at lambda equals 16, it gets so small that we basically don't see the difference anymore. So this is clearly working, and working reasonably well for things that we can actually put on the computer. So these are the sizes we can think about. Actually, what we've done is mostly between 4 and 10, because it's good enough and it doesn't take forever. So then we have all of the toolkit, so we can start trying to implement it. We need the algorithm, but the algorithm is fairly easy. We start out by generating a first state V0. And then we iteratively generate more states. And we're iterating states until the sum of the dispersions of the next states, the next best state, is no longer smaller than the distance between the states times some constant. The constant is not really important. It's order 1. Basically, what this is saying is we stop generating new points as soon as our states are overlapping each other significantly. At that point, we clearly have enough to cover the geometry within the precision that we can achieve. So we can generate pictures. And here we have a picture of the sphere at truncation lambda equal 5. And here we've got the sphere plus b. That is this other solution to the Heisenberg equation that I mentioned before. So this one is smaller than the sphere, and it's a little bit odd. So yeah, how do we get this picture? We've written the algorithm, then the graph embedding, and then we wonder, okay, so our new solution is embedded to be smaller than the sphere, but what does that mean? What is this new solution actually? So this, well, we were very happy about getting the pictures. It didn't actually help us as much as we were first hoping, and I'm still trying to figure that out. Which brings me to the last few slides, which are about ongoing work. Now, the first thing is, I mentioned earlier that I'm doing a linear combination of algebra elements, and I'm using a truncation of the spherical harmonics, which makes sense if I'm looking at a sphere, but I might want to at some point look at other things. Now, I'll have to generalize a bunch of things about my code if I want to do that, but the first thing that I want to generalize is I'd like to not use a truncation of the spherical harmonics, but the most general possible basis for an algebra, which, since it's just matrices, are actually just the matrices 0, 1, well, matrices with a single entry, not 0. And okay, that is easy enough done. I can put that in the computer and I can see what it does with my picture. Now, if I'm taking a picture for the sphere with the truncated spherical harmonics, that is the blue points. If I take the most general algebra generators, that's the orange points. So this works and is nice as a first step. And I'm working on the next steps to make it more general. The other bit that I've been trying to think about right now is I've got this new Dirac operator, which is given by the Dirac operator of the sphere, plus a constant times a finite operator. Now, when I gave a version of this talk to the virtual non-commutative geometry seminar, it was remarked that maybe this is some kind of a renormalization thing. Maybe this finite part does somehow do a renormalization type of stuff. So I was wondering, maybe adding something finite is of interest, but we've got this constant. To be a solution, the constant must be plus or minus 1/2, plus or minus depending on whether I've truncated at an odd or an even eigenvalue. But in principle, if I'm just making a picture of this, I'm not restrained to just looking at C equal plus or minus 1/2. Maybe I should just see what it actually does if I'm changing C. And then you can see this is actually the average radius. So the average distance of my points from the origin for the sphere, because that's easier than trying to plot a lot of different spheres and to compare them. Also, if I take an average, I can get rid of some of the fluctuations, which otherwise make it very hard to see a pattern in random signals. And so I've plotted the average radius against the constant C. And you can see that for n equal 42, that's truncated at 6. The radius is actually a little more than 1. We would expect the radius to be 1 for the unit sphere. For minus 1/2 or plus 1/2, it's a little less, it's 0.8. So that's what we saw on the picture before. And then as we keep going, it gets actually even smaller. So it stays roughly constant. And then here it goes very, very small. And I tried to understand that. I got a partial answer, at least so far. One part of the answer is that when I'm estimating my states, I'm using the dimension of my space-time. I estimate the dimension of the space-time using some formulas that are dependent on the eigenvalues of the Dirac operator. If I'm adding a constant part to the Dirac operator, that eventually changes the space-time dimension. So we see that somewhere between between minus 1.5 and minus 1, and between 1 and 1.5, the dimension of the space-time jumps from 1 to 2. At least that's what is detected. Now I have only got points here at minus 1, minus 1.5, and minus 2, and same here. So also if I was looking at larger n, then the region where I could actually look at this becomes larger. So this seems to be a truncation effect to some degree. And I actually made that plot earlier today, trying to finish the slides. But so I need to think about this some more.
And sorry, this blue curve, what does it represent?
This curve, this curve is the dimension that the algorithm estimates, and the orange curve is actually just the integer that the algorithm will round it to, because the computer needs integer dimensions.
Okay, so the dimension which you meant is the spectral dimension, and there is no abstraction for the spectral dimension to be non-integer, yes? So this curve is only the integer part of this blue curve, yes?
Exactly. The yellow, orange line is the integer part. The blue line is spectral base dimension. I don't want to call it a spectral dimension because that has a very particular meaning in physics circles. And then you've got an energy dependent dimension, and that is not what I was looking at here. But
okay, thank you.
Good. Okay, now the quick summary. Well, today I told you about exploring spectral triples using computer simulations. In particular, I wanted to tell you about the multi-matrix models from finite spectral triples, because there's still a lot of interesting work to be done there. And in trying to understand that more, I was starting to read about free probabilities. So I thought maybe if someone wants to explain or talk about this, that would be lovely. I made a picture of a spectral triple using the Kohn distance function, and in the process created states that are points, so that's useful. And okay, what are my future plans, at least immediately related to what I talked about today? Well, the first one is I want to do more visualizations. I've done a picture of a truncated sphere. Of course, it would be nice to do a fuzzy sphere and then a fuzzy torus. And then, well, I did simulations that gave me random finite spectral triples. Can I visualize them? Maybe I can see what they actually are. I'm in the process of making that work at the moment. There are some technical things that I need to sit down and calculate for myself, which I've avoided over the summer so far. Yes, I also want to get back to working on the integral over spectral triples, so these multi-matrix models. They have been resting a little bit while I was busy making pictures. And something that I was thinking about earlier, but keeps falling in and out of favor in my mind, is spectral triples as matter for other quantum gravity approaches. So yeah. Thank you.
So thank you very much, Lisa, for this talk. Do we have questions?
I have several more questions, if I could.
Of course.
So first of all, this is a quite general question. I'm somehow confused in this truncated picture, taking letting lambda goes to infinity corresponds to letting n to infinity, and the physical interpretation of this fact is that we are probing the space with higher and higher energies. Am I right? Or
yes.
Okay, so and also in this model for larger lambda, we get something which is more smooth in some sense. But this somehow is orthogonal to what is believed, I think, so in quantum gravity. In quantum gravity, people think that if you go to the smaller scales, somehow the space turns out to reveal some discrete structure.
Yes, that's a very good observation. So of course this is.
I'm confused with this.
So I'm probing with larger and larger energies. Something which I have already a priori put in is the spectral triple of a Riemannian manifold. So no matter how high my energies get, I will find more and more smoothness and that it is actually the Riemannian manifold. Now, if I was to do a quantum gravity model, then I would expect that at some large lambda, I will find something else, or I will just cut off, and then things would maybe get wild or just stop. But in this case, we are really just, it's
okay, so in some sense, we postulate that the space is described by a spectral triple, and then we run lambda, yes?
Exactly. So here we are really using lambda as a truncation of a spectral triple that is a Riemannian manifold.
I see.
But yes, that's a good observation that there are two different pictures that I might want to look at.
And if I could ask one more question, I would like to go back to the slide with this yellow and blue curve.
Of course. But could you also tell me who you are actually, since I can't
yes.
see it on my computer?
Adam Wegert, I'm remotely. I'm from Krakow.
Okay, yeah, sorry.
Probably you can see me because you are sharing your screen.
Exactly, that's.
Okay, yes, so my question is, you choose a concrete n, yes, and for this concrete n, you investigated what happens with this constant c, and you expect what behavior of this curve you expect if we go with n to some larger numbers with unity.
So if I increase n, then the region in the middle where things behave decently becomes larger. So
larger, yes.
So I mean, I should also add some more points to this plot in the fall off of the curve and smooth it out a bit. But I think that as n becomes larger, I'll get a larger region in the middle where things are well behaved, and then the fall off happens later. Partly based on the fact that if I increase n, then the part where the dimension falls off becomes at larger c. So.
Wow, so again, I'm confused because you mentioned that introducing this perturbation CB, it changes the first order condition. It spoils the first order condition.
Mm-hmm.
So I would expect that if you let n runs to infinity, the problem would be that the region for C which good behavior would be smaller and not larger. So I'm again confused. You see my point?
Yes, I see your point.
In some sense, for larger n, you have a larger region in which you can spoil the first order condition. So this is yes. Somehow strange.
Yes, it is actually.
But also interesting, very.
Yeah, I mean, there might. Yes, I will have to check more n. Yeah, I note it down, but I don't have an answer at the moment.
Okay. Okay, thank you. And thank you for the very interesting talk.
So maybe there are other questions? Yes, Gaëtan.
So if so, you showed some multi-matrix model coming from the random spectral triples. You can also look at the Feynman graphs of this multi-matrix model. That's going to give you maps which are colored. There's two colors, like in Bertrand's talk. There's a plus and minus on the edges. So it's some sort of Ising model with certain coupling. And this is a discrete model. However, you can look at very large search maps, and typically what you expect is going to converge to a random metric space, which usually has fractal geometry and is pretty complicated and also interesting. So somehow it will give another somehow rough geometry naturally attached to this model. And is it anything now? Is it in any way related to the geometry, that the way you approach it, the one of the random spectral triple, or how are these things related?
I'm not sure, because the Feynman expansion is, as far as I haven't looked at the literature in a while, but the Feynman expansions are usually for potentials that are not stable. So they are kind of the counterpoint to the simulations which I do, where I demand that my
Not stable, but you still expand around the Gaussian thing.
Yeah.
So what you wonder is maybe in the model that you wrote, maybe there's no point where some other Hessian is going to be definite positive. So actually there's no Gaussian measure on which to expand. Is that what you say?
I'm not sure right now. So our measure will be this action, and we'll put a minus sign in front.
So yeah, so I guess this action, it's if you part a G2, which is, let's say, negative big enough, then the Gaussian part is going to be positive definite. That's fine. Yeah, so yeah, exactly. So independently of the G2, you just fix it equal to 1 and you expand the rest, the quartic part. And that's going to give, a well-defined formal series on maps, Ising model map. And so it gives rise to a certain first discrete geometry, which when you can take the continuum limit.
Yes, but I think that the problem when doing those are these, but are those trace squared? But yes, I'm not an expert on the analytic matrix model things, so I'd need to sit down and have them.
No, these ones, I think you can actually even put that in what you expand. So you only keep the Gaussian measure coming from the first. And this part, we can discuss. I can tell you what it corresponds to combinatorially. Just certain pieces of the map are going to be cylinders, essentially.
Yes, I'd love to discuss that later. I don't think I can say anything useful about
nothing is
it right now. But
maybe I can say something. At least in 1-0 case, this has now been rigorously treated. So yeah, so I think phase transition can be established through resolvent methods by some variational techniques.